So we're going to take a look at level processing. This is following on from my first video, which I'll add in the links if you haven't already seen that. But what we're going to have a look at is how specifically non-contact level measurement devices analyze the signals and ensure that they're picking up on the right contents. The same could be said for technologies such as guided wave radar. They're analysed in a very similar way, but we're focusing on ultrasonic and radar for this particular example, not guided wave radar. The first thing we've got to understand is what we're actually looking at when we look at an echo profile. And what you tend to have is on PDM or the mobile IQ app, you'll have a trend that goes from left to right, where on the left hand side that's 0 meters, and then on the right hand side it's your empty distance plus a little bit of far range extension. And what you can see on the blue line, we have a transmit signal, and then we have something that we refer to on ultrasonics as ring down. So this is normally on ultrasonics where the near blanking comes into account. The signal then drops to its lowest point, which we call the noise floor. So ideally that noise floor will be 0 decibels. So the value on the left hand side, going vertically, the y-axis is decibels. Okay, so what happens then, it's easy to understand with sound. The signal travels through the air, this clicking sound that you can hear from an ultrasonics transducer. It hits an object, either liquids or solids. It reflects that back off, so it's like an echo, and then it comes back to the transducer. So we then get a signal, and that's a signal going vertically. It's not perfectly straight going up. Depending on the technology, it will be narrower, which you'll see as we go through this presentation. Once we've locked onto that, there's some sort of window, and again, Siemens call that the echo lock window, but that's there to ensure that if all of a sudden you get an echo 2 meters in front of that, it doesn't jump to that echo straight away. So if you've got a fill-in level, it should fill up gradually, and the window will track that change. So that's what we have, and then you can see this red line. So again, Siemens call that the time varying threshold, but basically anything below that red line is not analysed within the scoring mechanism of how to lock onto the true echo. So think of it as a filter. So straight away it filters out the noise floor, and it goes along, and anything blue that protrudes that red line is then scored on different algorithms, and some of those will be the height of the echo, the area of the echo above the red line, and whether that's the first or the last echo. So that's a look at the echo profile. I hope you understand it a bit more, but the next stage is, unfortunately, within our process, the strength of the signal coming back is not always the same, and all technologies are affected by this. Some of them are less severe than others, but a signal can get attenuated. I mean, it can get attenuated as well from the actual device aging. So let's look at that trend there. We can see the signals getting smaller. That could be because of dust, steam, foam, whatever. If our red line is fixed, then we have a problem with our signal going below that red line, and it's no longer analysed as an echo, because we've told it anything below the red line to ignore. The red line needs to be dynamic, and it moves with the change in process conditions in your vessel, and that's really important. And if you don't have that, then a lot of the times, some prime examples, condensation is a big one. Build up on the face, foam is another one. Attenuates the signal, and you'll lose the signal altogether. So that's the overview of the echo profile. So let's start looking at some real life echo profiles from our example. We're going to take a look at the echo profile from the ultrasonic level device, which is connected in the man cave. So you can see on the right hand side the joists. The joists are about 600 mil apart. We're missing the first few joists purely because the beam angle that's coming out of this hasn't travelled far enough for it to hit these first two beams. So we're not actually seeing the first two. It's the third beam that we're picking up. Then each one of these beams is about 600 mil apart. There is an opening on this one where it opens up into the roof space. So it sort of makes sense why this one is attenuated. And then we have the wall at the far end. So if we have a look at what we've learned so far, the blue signal is our echo coming back. This is our noise floor, so we can see that our noise floor is about 10 decibels. You can see the units on the left hand side. Then we have distance, and then we have the true echo. Here is our echo lock window, and then we have an echo marker to say where it's picked up on that. So we have the signal strength, and we also have the confidence. So this particular signal isn't brilliant, it's not bad, but it could be improved. And one of the ways to improve it is to shape around these blue, what we call false echoes. And you can do that automatically, or what I'm going to just show you now just as an exercise. You don't have to do manual, but we're going to do a little bit of manual TVT shaping. So here we have standard feature for Siemens level devices, manual TVT shaping. Now it's extremely rare that you have to do this, but I'm just showing you this as part of a training exercise. So remember what we said, the echoes are scored above the red line, and they're done on height, area, and whether they're first, second, or third, or last. So what we have to do is increase the score of the true echo, which is this last one, and decrease the score of these, because at the moment the overall score is shared amongst these. Now, to shape, we just move our point. I think you've got about, you can see there, 40 points, 42 points on the curve. And we can manually lift the red line. And the important thing is, when you've done this shaping, the red line, even though you've done it, it's still not fixed, it's still dynamic. So that's all we're doing. So I'm going to shape this red line, and then we'll have a look at what it does to our score. So remember, we had a score of 8, and we're going to try and increase that score by making these echoes more uncertain and our true echo more certain. So as you can see, I've done some very basic, if not messy, shaping, just to prove a point. Now, when you look at the algorithm, we're looking here at the largest echo, which is the amplitude, and the area. Okay, so we can't affect the amplitude of the echo. That's the signal coming back. That's how well it's bouncing off the material level. We can't affect where the echo appears in the list. What we can affect by moving this red line is the area of the echo, and that's what we're doing here by moving that red line. Okay, so it was just to show you it's all about the scoring mechanism behind this algorithm and how much of the signal is above the red line. So what we're going to have a look at next is the signals before we put the obstacles in place compared to those after, but just a little bit of a reminder of what we're actually looking at. I'm going to show you the test layout next. Here I am in the man cave, and I just wanted to give you an idea of what the radar and the ultrasonic device is trying to see. So at the moment the camera is pointing at me, and this wall is the target that we're trying to see. So I'm going to try and give you an idea of what we're trying to see. So this is our path, hello, to the radar, past the obstacles. So physically we are struggling to actually see the radar. It is behind the first obstacle, and you can just see it coming into view there. So if I get back in line, I can no longer see it. So it is a bit of a challenge, but some things we need to be aware of with radar. Radar works off a dielectric constant. Well, this material here hasn't got a high dielectric constant. There is a small amount of electronics inside, but not much. And this net, as you can see it, that's not very conductive. There are some small bits of metal inside, but really not much. Yes, put the Fireman Sam umbrella there, but again, it's not very conductive. The challenge really is this ladder. Trying to get past that ladder to see the back wall. Now, ultrasonics, it's a different challenge, because ultrasonics is looking for an echo, a reflection off products. So some of these, they're not going to give us too much of an echo back, but what they will do is prevent the echo coming through and going back at its full strength. So we'll have a look at the before and after echo profiles, and I'll go through some of the things that you can do to help you see that back wall. We will start with the LU240, which has a 10-degree beam angle, and as you can see, without the obstacles, this device is already struggling a little bit without me doing anything out the box. Have a confidence of 0, but a good, relatively good echo strength. I would expect it really to be up in the 80s, and that's because the signal is bouncing off all of these joists, and it looks like there's a bit of shelving at the bottom of my back wall, which I haven't seen in the video. Maybe it's picking up on that. Out of the box, the LU240 needs a little bit of help, but we have to remember we do have transducers with narrower beam angles, and really this is installed quite close to this structure. So now we'll have a look at the radar, the Citrans LR110, and this device is performing extremely well with all these obstacles. In fact, there's only one of the obstacles potentially out of all of them that's creating a larger echo, and that's the aluminium steps. You can see a slight attenuation in the confidence and a slight movement in the actual distance value, but considering what's been put in front of it, a 3 or 4 mil movement is absolutely fantastic, and at the moment this little radar's looking very, very good. We're back looking at the LU-240 ultrasonic device now with all the obstacles in the way, and we've got a slight increase on some of these. The one actually up closer is the one that's causing us the biggest problem, and because that is there, it's attenuating the signal, and the far end signal is getting attenuated the most, but it's not the end of the day for this device. We're going to have a look at something called auto false echo suppression. So if we go, sorry to jump around, if we go back to our device, our true level starts at 4.5 meters. So if we go to the auto false echo suppression wizard, set our, so everything before 4.5 meters we're classing as false echoes and fixed obstructions. So that procedure is now complete. All we have to do is take a new measurement. Here you have the echo profile after we've done the auto false echo suppression, and you can see it's moved the red line above all the obstacles, enabling us to lock on to the correct level. Now, I quite often get asked what happens when this signal travels up into this red zone. The beauty of ultrasonics is as this gets closer, it's actually going to get higher in amplitude and stronger because it's got less distance to travel. And the more obstacles our level goes past, the more signal we're getting back because less of it is being absorbed by the obstacles. So the closer that we get to the transducer, the bigger the signal. So as we start getting up, we should see this double in size, and then these false echoes really pale into insignificance. So there you have it, an overview of echo processing and the results of our non-contact level assault course with the various obstacles we put in the way. Both technologies work. The ultrasonic device required an auto false echo suppression learn, but the radar performed very well. But we would expect it in this case, narrower beam angle, and a lot of the obstacles had virtually no dielectric constant for it to reflect back up. But all that being said, it did cope very well getting past the ladders at the bottom end and just seemed to be unfazed by that obstacle. So I hope you found that useful. Thanks for tuning in, and please, if you've got time, register and click that bell button to get notifications of future video releases. Thanks for listening.